Hello, everyone. Welcome to my talk about what will be upcoming in C++23. I will tell you a little bit about the plans that had been in the committee about what we would like to see in C++23 and what compiler features actually made it in so far and what library features are voted in as of today. This doesn't mean it will really end up in C++23. The final vote is still not done yet, but we pretty much know what C++23 would look like. So I'm an electrical engineer. I'm doing software development for quite some time, and I'm also kind of a part of the C++ language committee. This talk is meant to be highly interactive. It depends upon you, what you will be learning and will be seeing in his presentation. C++23 is not a minor version of C++. As it turns out, it has lots and lots of new features. The material is probably worth 4 hours of talk. I have only 60 minutes, so it's totally up to you. So what was the plan about C++23? There has been a paper about what should be in there, and yeah, the idea was library support for coroutines. It was a modular standard library. It was executors, and it was networking. These were the most important features that had been lacking from C++20. And at least we should make a little bit progress on reflection, pattern matching, and contracts. You probably know contracts has been in C++20, but it didn't make it in the end. So let's do it in the next round. And there have been a lot of missing features in C++20 because C++20 was so large, we couldn't finalize everything in time. So we had a lot of backlog in C++20. Maybe we can clean up all our backlog. This was at February 2020 in Prague, when we were about to finalize C++20. Lots of people, I'm somewhere in the crowd. And this is what came afterwards. People were totally separate from each other. Working on a standard is not an easy task, and doing it in a pandemic is even more challenging. So let's see what actually is in the envelope right now. So the plan for C++23, once again, library support for coroutines. Yes, we did it. Actually, it's more like Corentin did it. We have a modular standard library. This is also done now. Executors, yeah, we made some progress. We had lots of discussion about executors, but nothing is finalized. Networking, just the same, but at least we have something since quite some time. We have the networking TS, and there's no progress any farther than that. Reflection, yeah, we have really good proposals on reflection, but nothing is in a final stage that you could say that it may be in 26. I'm not too optimistic about it. Reflection, contracts, nothing is in there. And so C++20 is also mostly completed, but not at the point where we want it to be now. So let's talk about core language features. We have Some really interesting major features like deducing this, also known under the term of explicit object parameters. We have a multidimensional subscript operator now. Interestingly, we have Lambda enhancements. What I really don't like about Lambda expressions is there's so much ceremony. We can get rid of part of the ceremony. We have consistent scope in there, and we finally have also attributes with Lambda expressions. We also did something on increasing the portability of C++, even as Robert was telling just an hour ago, C++ is not about portability. I think portability is important. So now the identifiers have to follow the Unicode standard Annex 31, also a work of Corentin. I really highly appreciate it. And also the encoding kind of stuff, there's much work done in the study group 16 about all these encoding kind of things. We have a bunch of minor new features like the size t suffix that makes our for loops now much safer if you're actually going to be using it. We have a few lesser restrictions in consteval functions. Maybe in the next round we may get rid of all of them. And I hope we also will get rid of consteval at all. In a future standard of C++, it should be the default. And we even did something in the preprocessor, even if you want to get rid of the preprocessor. Then a lot of things that felt more like bug-like features, like narrowing contextual conversions to bool. It makes your life a little bit more easier. And we actually did remove something. So what about the major new features and the implementation status? On the right column, you see in alphabetical order Clang, GCC, and MSVC, and the current status of implementation. Deducing this is probably the signature feature of C++23, is implemented in MSVC. You can use it today with current compilers. And Clang and GCC is catching up. On the other hand, multidimensional subscript operators, if consteval and the DDK copy in the language is only implemented in GCC and Clang, and MSVC is not that far ahead in the implementation. And there's also a new kind of thing, the extended floating point types, that may be interesting to all those people more in scientific programming. This is a very recent addition to the C++23 standard. No compiler has it yet. This is something like the bfloat 16 type that you may heard about, neural network inferencing and this kind of stuff, and actually giving floating points the exact number of bits that they should be represented with, up to float 128, as far as I know. From 16 to 128. This is quite a feature if you're into scientific programming or signal processing on this kind of stuff. So let's start with the first major feature, deducing this. In C++20, many of these member functions that observe values, for example, operator arrow or operator star, need to have a lot of overloads to be complete. You have to deal with constness, volatile, and probably also reference qualification, L-value reference qualification, R-value reference qualification. If you count all of them together, you're at 12 overloads you have to implement. This is no fun. And most people are lazy, at least I am, and usually I don't implement all of them. But now in C++23, we have the opportunity to explicitly get access to the object parameter. Up to 20, it has been a hidden parameter. It's called this. Because it's hidden, you have no control over it. You can't do anything other than use it, and it has to be a pointer. Pointer is just a mistake. It never has been meant to be a pointer. It had meant to be a reference. But at the time that the this pointer came into the language, C++ had no references at the time. This is the reason why we have the this pointer. And yeah, but now you can declare your object parameter just as you like to. Maybe you say you want it completely deduced, then you say type name self and call this object parameter here as a forwarding reference. And now the value category is deduced. You don't need any more overloads. And you give it actually a type that can be deduced. You can also give it an explicit type. And now with one single line, you have access to all the overloads that you have been forced to implement before. You see it here in an optional, the typical implementation that is only dealing with constants and reference qualification. You will see these more or less identical implementations of all these various overloads here. It's tedious and error prone. Many programmers just copy it over and forget something. And even better, you no longer have to use them as a reference type. You can make it a value type. So, for example, if you have a less than operator, less than a function object, then you can declare the function object parameter as unnamed. So the compiler knows it's not used here. You're only dealing with the additional left-hand side and right-hand side parameter in this operator call function. And now you don't have to have this hidden object. The compiler has to create an object somewhere just to form a reference to it. And no longer you have to do that. And this is an optimization opportunity for the compiler. Even more so, if you want to do something like mix-ins, you have certain types of functionality that you want to inject into your classes. Many times you usually use it by implementing it with the CRTP pattern. You make it this class, in this particular case, postfix increment, what you want to add to your arithmetic classes. And you implement it only once as a template and derive from it using the CRTP pattern. This boilerplate implementing this kind of thing is really difficult to understand, in particular for less experienced programmers. And it's really not how you want to express this kind of idea. In C++23, you can make it a templated operator ++ with a deduced object type. This gives the opportunity that when you derive your class from this base class here, which provides the functionality and the implementation of it, the compiler will figure out what the actual derived type is. So you no longer have to use all this boilerplate in the upper example here. So this is the intent that you want to express here is much more clearly formulated, and it's always correct. The next thing, probably also interesting for scientific operations, is the multidimensional subscript operator, also a work of Corentin. Up until 20, we could index with only one value as an indexing parameter. So people resorted to using the function call operator because you have as many parameters as you like to, but the function call is not actually what you want to use here. This is not a function call. The subscripting is something completely different. And in 20, we got rid of, or actually we deprecated the comma operator within the angle, the square brackets, so that you can re-grab our syntactic landscape and use multiple values into the square brackets with any number of arguments as we like, separated by a comma now. So we actually can express our multidimensional subscripting with the correct operator type and as many arguments as we want to. So instead of the function call operator, we do it like this and are done. If consteval, yeah, this is more interesting for people who do constant compile time programming. Who sees the problem here? Is there anybody who sees the error in this example? Yeah, okay. You know it. Nobody? We have if const expr and a function from the standard library which is asking the compiler, is this expression here evaluated at compile time? Of course it is. We said it so. If const expr is a compile time construct. The answer to this question is always true. All the optimized implementation for runtime will never be executed. This is a trap. Now we have if const eval we can now say that if we want to call a const eval, which is an immediate function which exists only at compile time, can be called this is a little bit you can call immediate functions from an immediate context. This is what I'm saying here in the middle part of the code examples here. You can call the function f from the function h because you're already in an immediate function context. But you cannot call it here because you are not in an immediate function context, which means the question if you are actually executing this code at compile time cannot be determined statically. And this means the argument e that's coming in here, it's difficult to explain if you're not in the committee here. The origin of the I must come from a constant value known at compile time, but this function doesn't know that here. It knows it is executed at compile time, but it doesn't know if the parameter I that's used here in the function call is actually coming from a constant that is evaluated and available at compile time. So this is illegal in C++20. You cannot express it this way. You're not in an immediate function context. You cannot call immediate functions here. In C++23, we have a new if construct. This is called if const eval. This has no condition there. It's just saying, okay, compiler, if this code is manifestly executed at compile time, you know it, you now can say, okay, this function call to f is now valid, because the call to g has to come with an argument that is constantly evaluated at compile time. The difference is a little bit hard to get around, but it's actually really, I have to go back a little bit. This is really important, and this is one of the major additions to the formatting library, where you can now formulate that the formatting expression and these parameters here are actually all constant and come from the compile time, and now you can validate your format strings at compile time. And this is one of the reasons why you can do that now. The next one, it doesn't sound that much, but if you look at the first 3 lines here, you want to erase all members in the collection here that have the same value as the first member in this collection. Does anybody see the problem here? Okay. Nobody? If you ask for the first element in this collection, you get a reference. And erase takes a reference. So at each round of the erase loop, it sees a different first element if you happen to erase something. So the outcome is completely undefined. What you have to do, you need to take a copy and put that in as the value that you want to erase from your container. In C++23, now you can say, explicitly give me a copy of the first one as an PR value without knowing the type. And this is the key takeaway from this functionality here. If you want to do it manually, this is the correct implementation if you want to know the exact type of the first element in your container. This comes in probably very difficult situation there you have wanted to do something like in-place operations and pass them on after the transformation into your functions. Now you can do these kinds of things much more efficiently because these PR values have also the ability just to decay into the copying of the function parameter, and so you get best of both worlds here. This is the science behind it. Maybe it's a little bit less interesting. This was one of the missing pieces in up to C++20. Now you have it. These extended floating point types I've been talking before. Up till C++20 we had double float and long double. On MSVC you didn't even have long double. And now you can have float 16T up to float 128T and V float 16. But these are not mandatory. Please keep this in mind. Lambda enhancements, well, let's look at these examples here. These three examples here return an int, and this int is deduced from the return value. That's the j in here. The j is an int because we're capturing the j and initializing it with a 0 literal. You see, in some cases you have to put the parentheses in. If you want it mutable, you say mutable. If you have to say mutable because by default it's const, so you can't increment it. But if you want to increment it and don't want to give it a parameter, this is invalid syntax in C++20. As soon as you qualify it with mutable, you have to put the parentheses in here, even if you don't use any of the parameters. And maybe you want to make sure that you have certain attributes like no discard. This is a made-up example. This is not valid syntax. You had no chance to express this. Now, if you explicitly say what the return type is supposed to be, you no longer deduce it from the return of the expression. Here in this particular example, you say decal type j. Everything is fine, still. But what happens if you introduce a variable called j in the surrounding context? The problem with that is this decal type j does not bind to the capture j in the capture clause, but it does bind to the outer j. So suddenly, your lambda expression is no longer returning an int as before, but now it's a double. And this is completely surprising to almost everybody who is using lambda expressions. In C++23 now, we bind this decal type to the capture j in the capture expression, but unfortunately, we can't do it in a perfect way. There are some edge cases that this doesn't work and because of syntax, but now you usually can take it for granted that you get exactly the result what you're expecting, so that the j in the decal type actually binds to the j in the capture because it's nearer to the core of the lambda expression and the resulting closure type. You can also get rid of the unnecessary parentheses, even if you have qualifications like mutable, and you can put attributes in here. The portability thing. The identifier syntax, I've been actually talking about it. This is also a defect report against C++20. So you expect your compilers to switch the behavior here. Then we have multiple other improvements like handling of white spaces at the end of spliced lines or literal concatenation and literal encoding and all this kind of stuff, and UTF-8 encoding as a mandatory supported source code encoding. white characters and encoding. There have been so many places where your source code probably didn't do what you wanted it to do. You believed it to do because you were depending on implementation-defined behavior. And yeah, the last part. WRT is no longer required to encode all code points that you have in Unicode. Maybe nobody knew that all C++ code compiled by Visual Studio was actually not valid C++ code, because it was violating this particular requirements that has been in place up until C++ 20. So this, as an example of this identifier syntax, quite famous in conference slides, this is no longer valid code. Who sees the problem in this particular example? Michael Case is pointing at it. At the end of the line, you have a space, and right before the space, you have a backslash. So the backslash usually indicates a line continuation. So line 9 becomes concatenated to the end of line 8. But only if the compiler ignores the space at the end of the line. So depending on the compiler, the value is either 0 or a lead. Up until C++ 20, you could concatenate strings with different encodings. Does it make sense? Probably not. Each compiler is handling this differently. Luckily enough, in C++ 23, none of this is legal anymore. Your compiler will complain, hopefully. Here in this particular example, we are testing if A is actually encoded with a value of hex 4 and 1, but once at the preprocessor and once at the language level. Nobody guarantees that the outcome of this equality comparison is the same. Actually, some implementations took this to differentiate between abscisic encoding and ASCII encoding. Now the compilers are required to return the same result by these comparison expressions, no matter if you're doing it in the preprocessor or if you're doing it at the language level. Yeah, then there are many other things that are less interesting here. The most important key takeaway from here: your compiler must provide a means to take source code as UTF-8 encoded character streams. There was a lot of discussions around that. Are there streams now, character streams?
Yeah, just know that UTF-8 works.
Yeah, okay. Just if you happen to have your source code encoded in UTF-8, now you're safe, and the meaning of your source code is well defined and no longer implementation defined or whatever it has been in the past. Then you had all these weird encodings. All of these were not doing what you probably expected it to do. Now we say all of that is ill-formed. This is quite a surprise. It was also a surprise to me. Line 1 in the upper example is one character. Even though a char can never have a value that can be expressed by this hexadecimal encoding of a string. This is not possible. Actually, in the documentation of the Microsoft compiler, they say, express it this way, that you really mean these are two characters. Now you have syntax to actually express, okay, this is character 1, this is character 2, without ambiguity in them. Yeah, and if you're really into be explicit about what kind of character you're referring to, you can now use the names from the Unicode standard and say, okay, you want a Latin capital letter with a macro, or combine it with a graph accent. You can express it without resorting to hexadecimal lookups from any table. Suffixes for size t's, yeah. I could talk a lot about it, but it will probably take too much time. The problem with current code is if you want to have a for loop that takes a initializer and deduce the type with an auto, the deduce type is not the same type as the result from the size operation of the container, depending on the bitness, the bit width that you're compiling for. This is either a truncation, or it can run into if you don't want to run into the problem with the 64-bit truncation here, and you say, okay, people say use an int, then you have the problem with mixed comparisons between ints and unsigned ints, and it also depends on the promotions and this kind of thing. So this is not a secure coding in the face of various bitnesses, and so you should not do that. And to help you in doing this, we have now a way to actually express size t types which match all the bitness of your compilation. If it's 32-bit or if it's 64-bit, it all gives you the correct size now. Yeah, we will probably skip this here. This is not too interesting. Implicit moves, yeah. We have a lot of things that we actually automatically move up until C++20, but there are still some corner cases where you would prefer to really move return values out, but you can't. In C++23 now, there are more use cases where this happens all automatically, but explaining them all here is way too much. Please look at the paper if you're interested in. Also, the static operator is not that much. Portable assumption, is Timo here? Okay, if not, we skip it. Compatibility with C, yeah, we have new directives like elifdef and elifndef. This is probably not too interesting here. We have now the ability with hash warning to give warnings during the compilation. For example, okay, this is deprecated, will be probably going away at some time. You can express it now in your code, and this will not stop the compilation anymore. Because if you have been doing this with a hash error or a static assert, it would immediately stop your compilation. Now you can put a warning into your output of the compiler. Yeah, the rest is more or less expandable. And narrowing contextual conversions to bool, yeah. If you had expressions like these here, all of them are evaluated at compile time. Up until 20, many of these compile time expressions, in particular the Boolean ones, were considered narrowing conversions. And narrowing conversions are not allowed at compile time. So you had to resort to really awkward formulations to check for Boolean flags or sizes of or the outcomes of integral operations. Now you can express it like you would do at runtime code and no longer have to go through all of these hoops. I really don't want to talk about this one here. It's just it's a gotcha. This is more important now. You can have compile time argument deduction from inherited constructors. In C++20, if you were using derived types, where you were actually relying on inheriting constructors from the base classes, compile time argument deduction wouldn't work. Strange reasons. It's actually only about wording. In C++23, this is fixed now. This is probably less interesting for the actual. Here, this is a gotcha that you have to be aware of in C++20. If you have an equality or inequality operator in your class, and you forget to const qualify these operator functions. Line 6, the outcome of the inequality comparison between two PR values constructed here is totally undefined behavior. Actually, it's more like implementation defined, but it's no different. One compiler would say, okay, these two PR values are the same, probably what you were expecting. Other compilers would say, no, there are different instances. They're not the same. And the problem is the lack of the const qualification of the operators here. Good for pub quizzes. In C++23, now we got rid of all of this. It's no longer ambiguous. Charity has a long history of discussions. And actually, many changes has been happening in 17 and 20. And you had gratuitous incompatibilities with C. And now we say, okay, at least for the most obvious situations where you want to have char 8 UTF-8 encoded literals, we avoid all these discussions and say, okay, this is fine now. You can assign U8 encoded strings to unsigned char arrays. And this is probably what you really want if you have header files from C. Did you know that we had garbage collection in C++? Since C++11. Nobody implemented it. Did you know that the layout order in your classes was probably not what you were expected them to be? This particular example can have 6 different orderings of the members in the class layout. At least according to the standard. But no compiler took advantage of this, so we got rid of this. Now it's clear it's the first order. Let's come to the library, and I will probably defer to Corentin because he's on the library working group. We have a couple of new major features like stack trace, expected, generator, print, and the modular standard library. We have increased the compatibility to C, improved chrono format string and string view. The string is the endless story. Every standard we have more member functions in string. We have lots of fixes in ranges and in particular in use. We had made progress on const for all the things. We had a lot of usability improvements when it comes to optional and heterogeneous arrays and lookups and tuples and pairs and this kind of things. And the library also decided we no longer want to support garbage collection. So stack trace library. This is modeled after the Boost stack trace library. Maybe some of you are familiar with the stack trace library. So we have it in the standard now. If you want to use this, for example, if you're at a certain point and want to put a stack trace into the log, now you can do it with just the standard functionality in there. Expected, one of my favorites here. I guess all of you are familiar with optional. With optional, you can return a value of a certain type and also can return the fact that you don't have a value available at the return. But with expected, you can express a little bit more. You can ever return the expected value type. And if you happen to not be able to produce a result, you can explicitly express your disappointment by some type that you want to use here in this. Maybe this is a string that you can write in what's the problem, why you can't produce a result. Or you use a std error code or whatever it has. You can decide on how you express your disappointment, why you can't produce a valid result. You have all the accessors to figure out if you have a valid result or you have a problem. And you can also use it in if expressions so that you process the result only if you have actually got one. Another function that is interesting in particular for people who have to communicate data structures between systems with different architectures. One of them may be a big endian, the other one may be little endian, and you want to move these data structures across a network connection or whatever it might be in this particular case. Now you can byte swap using the standard library, and the advantages over the C library, the H2S and H2N and all these C functions that you have been using in the past for that is this is const expr, doesn't introduce undefined behavior, and it works only with integral types where it's safe to use. Move only function is also interesting. I'm using it right now in my code because now you can say in your callbacks that you probably pass into your different parts of your code that you expect them to be no except. You couldn't do that with a std function. You had no guarantee that the function that you were calling on behalf of these function wrappers is actually not producing an exception while you were calling into that. Now you can express it, you accept only functions that will not produce exceptions during the function call. There are even more aspects to use move-only functions. I will not go into details here. This unreachable library function is interesting if you want to squeeze the last bit of performance out of your switch statements, because in the C++20 example here, the compiler had to put extra code in here if there happen to be inputs that are not 1, 2, 0, 1, 2, or 3, because of implementation details. In C++23, you can say you guarantee that no invalid value will come in here, and you say std unreachable, and the compiler say, okay, I believe you, I will not produce any code for handling out of bound values in the parameter. This is my particular favorite. Formatted output to the terminal. Not only you get compile time checking for the format string, but also you get with the std print function in C++23 a guaranteed encoding. So the emoji bucket that you're seeing in the upper example will no longer happen if you're outputting formatted strings to the terminal. This means also Unicode handling is really baked into the library at this point. And this is a common theme throughout 2023 to implement much more Unicode handling in a safe manner and in a consistent manner. Yeah, I really have to say study group 16 has been extremely productive here. Corontor, is there still anything left to do?
Oh, yeah.
Okay, expect more on that in C++26. And now we have it. Yes, standard library modules. In C++20, yeah, you need a fold operation and fold algorithm. Oh, it's not called fold, it's called accumulate, and it's not in the algorithm header, but in the numeric header. Who knew that? Now with the library modules, the whole library is in one module. You no longer have to figure out which headers you have to include. And you also get the performance benefit of using modules here. So you have two flavors of it. flavor 1 is just import stud, probably what most people will be using in the future. It's everything of the C++ headers and the C wrapper. If you really need the semantics and the namings from the C standard library, which is also part of the C++ standard, you can use stud compat, so you get all of the headers that are actually standardized in C++. Another thing, really important in my opinion, and also a reference implementation by Coronta, once again. Stud generator. Who is familiar with coroutines? Okay, quite a few. What do you think about the library support in C++20 when it comes to coroutines? Are you happy? Correct answer, it doesn't exist. With stud generator, you can put a range facade in front of your coroutines, which means if you have a coroutine that produces a sequence of values, you can now just say this function, for coroutine is a function, is returning a generator, and on the call side, you can, for example, put the range generated lazily by the coroutine can be passed into a piece of code that operates on this range, for example, puts it into a container or transforms it or whatever it has to do with it. Even can use it in a range-based for loop, and at each iteration step, the coroutine behind this generator facade will produce a new result. So the usage of coroutines to produce a finite or even an infinite amount of return values can now be expressed through the standard library. And this is extremely helpful if you want to do lazy operations. We also have flat maps and flat sets. Everybody who is familiar with the boost flat map and flat set, we have it now in the standard library with a slightly different ordering where how we store the kind of things. Yeah, the standard always has to be a little bit different. Yeah, then I have a lot of C compatibility things, but this is not that interesting unless you are really a use case for that. This is interesting for people who have to deal with C parts in their code. No, I don't know if you have been aware that the C headers in C++ were officially deprecated. So if your lawyers in the company said you can't use deprecated things in your code, we're probably not that happy. And this is the reason why we decided to no longer deprecate it, but we officially discourage it only. So this is more a lawyerly kind of thing. Let me see how far we're in. Yeah. You're probably at the end of the talk, but this is something that I will go through because I think it's really interesting. This function called stud to underlining for enumerations. Assume in the beginning we had an enum class with some values. we had a function that takes in this enum class as a parameter and is unwrapping it and putting it into an unsafe function that takes just an integral type, like an int here. We usually do this with a static cast, and yeah, at this point it's mostly harmless. But some point later, somebody changes the enumeration, has an additional value in there, so that the amount of bits that have to be allocated to the representation of this enum changes silently. And to accommodate to that, the person said, okay, I give it an explicit type. I say, this is a new 23 now. But the implementation of the function wasn't changed. It still says static cast int, undefined behavior. Even farther along, oh, yep. The type, the type of the enumeration in there is changed. The problem is, before that, here we said, this is not highlighted here in the upper example. We cast it to the underlying type, to the underlying type explicitly ABC, and if this changes later on, you have another enumeration type here, which is no longer the same as has been before, and we still have this underlying type unchanged here. Now we have another problem. So the correct solution in C++23 is let the compiler deduce everything here, use the function to underlying type, and now the conversion from the enumeration type, if it's a class type, if it's a non-class type, or if it's if there's an explicit underlying type given there, is no longer important here. So using this will give you always the correct answer. Yeah, and I think I have squeezed as much as I possibly could into this talk, but as far as I see, we are out of time. If you have questions about additional new features, I've been giving a list, then come up to me. I can explain probably more of it, but unfortunately, I don't have 4 hours of time to explain everything in all detail, and nobody was raising a question. I am probably done with telling you at least parts of the new language features of C++23. Thank you very much.